Use the limit definition of a definite integral to prove that for integrable functions f of x and g of x on the closed interval between a and b, the integral from a to b of f of x dx equals the integral from a to c of f of x dx plus the integral from b to c of f of x dx for all c within the closed interval a and b, as in c somewhere in between a and b. Right, so if we just draw a little picture of that, what that means, you've got so a and b. Again, I'm just going to represent this as a nice simple positive continuous integral. Well, it tells me it's a nice and integrable anyway, but it doesn't tell me it's positive all the time. So some kind of function like that, and it tells me that c is somewhere in between a and b, so let's just put c here. And it's basically asking us to prove that the whole area, the integral between a and b of f of x dx equals the integral between a and c plus b and c. You can see clearly, of course it is, so the integral between a and c plus b and c, so c and b. Dx plus the integral between c and b. Okay, so the limit definition comes from the Riemann sums. So the limit definition is that the integral between a and b of f of x dx will equals the lim as n approaches infinity. Remember, this is all about rectangles. Integration, it's about adding up loads and loads of rectangles, and as the number of rectangles approaches infinity and the width of those rectangles approaches 0. So it's the limit as n approaches infinity of, well, it's b minus a over n. Remember, b minus a is the width of the whole interval, and over n, if it's divided up into n sub-intervals, then that's just the width of each one. So the width of the rectangle times the sum from I equals 1 to n of the heights of the rectangles, so f of xi, literally the height of each rectangle. So that's the limit definition, right? So what we're going to do now, so we're going to use the limit definition of the integral between a and c and b and c see if we can arrive at that. Okay, so so between a and c, the integral of f of x dx plus the integral between c and b of f of x dx, well, using the limit definition, that must equal the limit as n approaches infinity of, well, the first one, it's going to be c minus a over n. C minus a over n times the sum from I equals 1 to n of f of xi, and the height of each rectangle, plus, then we do the same thing for BC, the lim as n approaches infinity, b minus c over n times the Riemann sum of the heights, times the sum of all the heights of the rectangles, so the sum from I equals 1 to n of f of xi. Close that off and see what we can do. You should be able to, if you look kind of like a common factor, you've got this. In all of this, you've got this Riemann sum bit, so the sigma part of f of xi is common to both terms, as is the over n. So really what you've got is, you've got the limit as n approaches infinity of, well, if we take the sum and put it here, so the sum from I equals 1 to n of f of xi, and that, because that's in both, so the first time it's c minus a over n, and it's plus b minus c over m. And that can look like that. And then because you've got this common denominator of n, I probably could have done that in one step, but it's good. I think it's good to show. So now you can say, well, that's the lim as n approaches infinity of, well, this is going to be c minus a plus b minus c. C minus a plus b minus c. So it looks like, it looks like we're going to get some cancelling, times this sigma that we've had the whole time from I equals 1 to n of f of xi. Right, so the c's disappear, and you end up with minus a plus b, which is the same as b minus a. So that equals the limit as n approaches infinity of, well, it's b minus a over n times the sum from I equals 1 to n of f of xi. And looking at that, you can see that's clearly the limit definition of the definite integral of f of x from a to b. That equals from a to b the integral of f of x dx. So we've now proven it using the definitions. It is a lot of working out, and you do wonder what it's all for, but that is how you do it.